are in an era where technology is at its peak. We use apps that are constantly handling data by searching, adding, removing, all in real time. But have you ever wondered how to keep things running smoothly even when data keeps growing? Meet the red-black tree. The red-black tree is a self-balancing binary tree that maintains logarithmic time complexity for insertion, deletion, and search operations. In this video, we will look at what a black tree is, how it works, and where it's usually used. Okay, to start, let me give you a scenario. So imagine you are building a messaging app with a growing contact list. You need to find a contact instantly, add new users as they sign up, or remove inactive ones. A binary search tree might seem like a smart choice. It keeps everything sorted and makes lookups fast. But here's the issue. If most users sign up in an alphabetical order or by timestamp, the tree becomes heavily unbalanced. Instead of branching efficiently, it stretches into a long, narrow path, and just like that, your big O of log n speed drops to big O of n. Skewed, unbalanced, and slow. What should have been a big O of log n performance now becomes a big O of n. To maintain consistent efficiency, even with sorted input, we rely on a self-balancing structure called the red-black tree. So the red-black tree is originally introduced by Rudolf Bayer in 1970s and later refined by Gubias and Sedgwick. Red-black trees are also the type of balancing binary search tree. They automatically reorganize themselves during insertions and deletions, keeping the tree's height in check and the performance consistent. How does the red-black tree stay balanced? The key lies in two things: coloring and a set of balancing rules. Every node in a red-black tree is colored either red or black, and the tree must follow these specific properties. Number 1, the root node must always be black. Number 2, every leaf which is nil is black. Number 3, if node is red, then its children are black. Number 4, every path from the node to any of its descendant nil node has the same number of black nodes. By following these specific properties, the red-black tree guarantees that no branch becomes too long, ensuring that the height of the tree stays logarithmic relative to the number of elements. And when the rules are broken, say after an insertion or deletion, the tree fixes itself through rotations and recoloring. And as a result, even as your data grows and changes, search, insert, and delete operations all stay at big O of log n time.
The red-black tree's strength lies in its predictable performance. Searching, which takes big O of log n. Inserting also takes big O of log n. Deleting big O of log n. So, log n means that even if you double the size of your dataset, you only need one extra step to finding something. So while an unbalanced binary search tree might take hundreds of steps, a red-black tree will take just 10, 20, or even 30 with millions of entries. These time complexities aren't just theoretical, they matter in real-world systems. Take for an example, an e-commerce platform. Products are constantly being added, updated, or removed. Customers are searching, filtering, and sorting thousands of items in real time. You can't afford performance drops when the product catalog grows or changes rapidly. A red-black tree helps keep those operations smooth and predictable, regardless of how the data comes in randomly or sorted. The structure maintains balance and keeps operation efficient. So that is why it's used in systems ranging from inventory databases to financial transaction where consistency and speeds are critical.
So now we know the background and the speed of this algorithm. Let's put the theory into an action. Let's imagine that you are designing a digital organizing system for a hospital emergency room. Every patient who walks in gets assigned to a priority number. The lower the number, the more urgent the case. Your system needs to insert new patients in real time. Always find the most urgent patient quickly and remove patients as they're treated or moved. And that's the perfect job for a red black tree. It keeps the data organized per priority and balance so operations stay fast even during a rush. So let's walk through a live example with 5 patients entering in the following order, with their priority levels, which is lower is more critical. The patient name was Alice with a priority number of 30, Bob with a priority of 15, Charlie with a priority of 25, Diana with a priority with 10, and lastly Ethan with a priority of 20. And we'll insert them one by one into a red-black tree. So, step 1. Let's insert Alice with a priority number of 30. So, at first, the tree is empty. And since Alice was the first patient with a priority number 30, Alice becomes the root node. According to the red-black tree, the root must be black, so we color her node black. Next step, we insert Bob. Bob has a priority number of 15. And as you can see, 15 is less than 30. So Bob goes to the left of Alice. Since the role of the red-black tree is that new nodes are red by default. Alice is black and the Bob is red, so no rules are violated. Step 3. Let's insert Charlie. Charlie has a priority number of 25. Since 25 goes between Bob and Alice, we place it to the right of Bob. Since it is greater than 15 but less than 30 and Bob is red, so is Charlie is red. As you can see, there are 2 nodes in a row, and that's a violation. So to fix this, we should recolor Bob and Charlie to black, and Alice, which is their parent, to red. But as you can see, the root node is red, which violates another rule, which is the root must be black. So to fix this, we recolor Alice back to black, which results to Alice being black, Bob being black, and also Charlie being black. Step 4. Let's insert Diana. Diana has a 10 priority number. 10 is less than 15, so we will insert it as the left child of Bob. Diana is red, Bob is black, so no rules are violated. Step 5. Let's insert Ethan. Ethan has a priority number of 20. Since 20 goes between 15 and 25, so it becomes the left child of 25. Since according to the tree, there are no red-red violation, and so that no recoloring rotations are needed. So the final tree must be 30 as black, 15 as black, 10 as red, and 25 as black, and 20 are red. With these changes, the tree remains balanced and no fix is necessary. So let's move on the results and observation of this algorithm. What did the tree do right? At each step, the red-black tree made local fixes, such as rotations or recoloring, to avoid cascading slowdowns. Even after 5 inserts, with a mix of high and low priorities, the tree remained shallow and ordered. Now, if a doctor requests the highest priority patient, the system finds Diana, with a priority number of 10 almost instantly, regardless of the patient's order. And if the yana is discharged, the deletion process kicks in, followed by a rebalance if needed, and the red-black trees might rotate or recolor again, but the structure remains tight and efficient. This examples shows how red-black trees quietly work behind the scenes, ensuring operations are always predictable, even in messy real-world data. Regardless of this example, we also observe that insertion took an average of 0.002 milliseconds and the deletion took about 0.003 milliseconds, which means using this algorithm is very efficient and fast.
So let's talk about the result. To really understand how well a read block tree performs, we tested it against two other popular self-balancing trees such as AVL trees and splay trees. So what is AVL trees? AVL trees are stricter about keeping the tree perfectly balanced, and the splay trees are great if you're accessing the same data repeatedly. We ran through of these three challenges to see how they handle real work such as adding, deleting, and finding data, just like any system that deals with users, messages, tasks, or records. Here's what we measured. It is how fast each tree can insert and delete data. How much work the data tree does to stay balanced measured in rotations. How much memory each one uses. And the last one is where each one works best. We didn't just test a few numbers. We simulated real situations. H3 was given thousands to a million items to handle. We mess up the data, sometimes random, sometimes already sorted, which usually causes problem in regular trees. H3 handled a combo of 40% exertions, 40% deletions, and 20% searches. Just like what's expected in real system, we use tools like Valgrind and JProof to track performance and memory. Everything was done on the same computer set up to make the results fair. Here's a quick comparison of the three trees. The algorithm is red-block tree. The enter speed is fast. The delete speed is fast. The rotations needed is medium to 3 per 1000 OPS. Memory use is moderate. The base use case of red-block tree is great for system with lots of changes. Next is AVL tree. The insert speed of AVL tree is slower. The delete speed is slower. The rotations needed is high, 4 to 6 per 1000 OPS. Next is memory use. This is low. And the base use case of AVL tree is best for read-heavy apps. Next is splay tree. So the splay tree insert speed is varies. The delete speed is varies. The rotation needed is low. Memory use very low. The base use case of the splay tree is best when accessing same data often. Red-block trees are fast and consistent. They do a bit balancing, but not too much. So they stay quick even with big data. The AVL trees are super balanced, do extra work to stay that way. That makes them slower when you're adding and removing lots of data. Display trees are unpredictable, great when you keep accessing the same data, but slower in random situations. Our test, the red-block tree was the most reliable overall. That's always the absolute fastest in every category, but it handles changing data really well. It's exactly what many real apps in system did.
So why black trees matter? So basically, red-black trees are all about practical efficiency. It offers a practical balance between performance and structure. Unlike AVL trees, which enforce strict balancing through frequent rotations, red-black trees allow a controlled amount of imbalance. This results in fewer rotations on insertions and deletions, which reduces overhead, especially in the systems with frequent data updates. They also maintain a time complexity of big O of log n for search, insert, and delete operations while minimizing restructuring. This makes them a well-suited applications where maintaining predictable performance is critical even as data grows or changes dynamically. So the key advantages of this algorithm is that it has a fast performance across searching, inserting, and deleting. It is balanced enough to stay efficient without extra effort. It is scalable for both small and large datasets. It is fewer structural updates than stricter trees like the AVL. But of course, no algorithm is perfect, and the red-black tree doesn't escape that. It also has disadvantages such as, first, it is more complex to code. Implementing red-black tree is more complicated than a basic binary search tree, as this requires understanding of rotations and color rules. Second, extra memory use. Each node stores a color, red or black, which adds a bit of a memory overhead. Lastly, not always the safest for read-only scenarios. If your app rarely changes data and mostly just reads it like a search engine index, AVL trees might be slightly faster in this scenario due to their tighter balance. So, while red-black trees are great for dynamic systems, they are not always the first choice for simpler or highly red-focused applications. Red-black trees stand out for their balanced trade-off between strictness and efficiency. They maintain logarithmic time for search, insert, and delete operations while requiring fewer rotations than the stricter self-balancing structures like AVL trees. In benchmark testing, red-black trees constantly outperform AVL trees on their mixed workloads, particularly when handling frequent insertions and deletions, both with random and sorted data. Compared to splay trees, they offered more predictable and stable performance, especially at scale. Their practical efficiency makes them a preferred choice in performance-critical systems, including Linux process schedulers, file system indexing, Java Stream App, and tree set implementations. So in the real-world production environments, red-black trees are chosen not for theoretical elegance, but because they perform reliably under pressure. Red-black trees aren't just a way to store data. They are a smart design choice, quick, steady, and reliable. So if your project needs to handle frequent updates while keeping operations smooth, this tree delivers consistent performance. So in summary, red-black trees offer a reliable way to keep data organized when it's constantly changing. They aren't perfectly balanced, but that's intentional. It reduces complexity while keeping operations efficient. They are used in real systems because they provide consistent performance even as input size grow or data changes frequently. So if you're building a software that needs to handle updates quickly, like indexing, logging, or resource tracking, red-black trees are a solid choice.